Fundamentals of Compute Resources offered by Amazon Web Services, AWS. Compute is a large element of the AWS infrastructure, and it's likely to be one of the first service types that you will use or are already using. There are a number of foundation services that AWS is built upon, compute being one of them, in addition to storage, database, and network. This course will focus on compute resources. To learn more about the fundamentals of the other foundation services, please see our other AWS fundamental courses listed here. As this is a beginner's course, I will cover all compute elements from the ground up, ensuring you have a full understanding of each service and features discussed. Before we start, I'd like to introduce myself. My name is Stuart Scott. I am one of the trainers here at Cloud Academy, specialising in AWS. Feel free to contact me with any questions using the details shown on screen. Alternatively, you can always get in touch with us here at Cloud Academy by sending an email to support@cloudacademy.com, where one of our cloud experts will reply to your question. This course has been designed for anyone with an interest in AWS and looking to learn about the different compute fundamentals of the platform. This is a beginner's course, and so if you are new to AWS and are looking to understand what compute is and the resources and services that are classed as compute, then this course is for you. This would also be advantageous to those looking to take any of the associate level AWS certifications. Throughout this course, I will discuss a number of different compute services and features of AWS that fall under the category of compute resources. As a result, I've broken the course into the following lectures. Starting with what is compute in AWS. Before we can discuss the different compute resources available within AWS, it's important we understand what compute is. Elastic Compute Cloud, known as EC2. This is one of the most common compute services, and as a result, this will likely be the longest lecture, as I want to cover a lot of the elements around EC2 to ensure you are aware of how it's put together and how it works. Amazon ECS, the EC2 container service. Within this lecture, I will provide a high-level overview of what the EC2 container service is and how it relates to Docker. Amazon Elastic Container Registry. In this lecture, I explain how this service links closely with ECS to provide a secure location to store and manage your Docker images. Amazon Elastic Container Service for Kubernetes, EKS. Here I look at how EKS provides a managed service, allowing you to run Kubernetes across your AWS infrastructure without having to take care of running the Kubernetes control plane. AWS Elastic Beanstalk. This lecture will provide an overview of the service, showing how it's used to automatically deploy applications using EC2 and a number of other AWS services. AWS Lambda. This lecture covers the Lambda serverless service, where I shall explain what serverless means and how this service is used to run your own code in response to events. AWS Batch. Here I will provide a high-level overview of this service that relates to batch computing. And Amazon Lightsail. Finally, we will look at Amazon Lightsail, a virtual private server solution used for small-scale projects and use cases. Throughout this course, I will provide some demonstrations on how to perform certain tasks. In addition to this, I will also add a number of links to our labs that relate to the topics which will allow you to carry out configurational elements in a live AWS environment without any additional cost to you that you might incur performing the same on your own AWS account. Completing the labs highlighted will enable you to get hands-on practice embedding what you have learned throughout the course. Once you have completed this course, you will understand what is meant by compute, you'll be able to explain each of the compute resources used within AWS, and you'll be able to select the most appropriate compute resource depending on your business requirements. If you are new to cloud computing, then I recommend you take our existing course, What is Cloud Computing, to give you a foundation of cloud computing principles and terminology which will be used throughout this course, and you can find this course here. Feedback on our courses here at Cloud Academy are valuable to both us as trainers and any students looking to take the same course in the future. If you have any feedback, positive or negative, it would be greatly appreciated if you could send an email to support@cloudacademy.com. That brings us to the end of this lecture. Coming up next, we are going to answer the question, what is compute in AWS? Hello and welcome to this very short lecture where we are going to answer the question, what is compute in AWS? Before we begin to explore compute services, resources and features, we must first understand what is meant by the term compute. So what is it? Put simply, Compute resources can be considered the brains and processing power required by applications and systems to carry out computational tasks via a series of instructions. So essentially, compute is closely related to common server components, which many of you will already be familiar with, such as CPUs and RAM. With that in mind, a physical server within a data center would be considered a compute resource, as it may have multiple CPUs and many gigs of RAM to process instructions given by the operating system and applications. Within AWS, there are a number of different services and features that offer compute power to provide different functions. Some of these services provide compute which can comprise of utilizing hundreds of EC2 instances or virtual servers, which may be used continuously for months or even years, processing millions upon millions of instructions. On the other end of this scale, you may only utilize a few hundred milliseconds of compute resource to execute just a few lines of code within AWS Lambda before relinquishing that compute power. AWS Lambda is a serverless compute resource in AWS, and I'll cover more on this service later in this course. Compute resources can be consumed in different quantities for different lengths of time across a range of categories, offering a wide scope of performance and benefit options. So it will really depend on your requirements as to which compute resource you use within AWS, and this course will discuss them all, allowing you to decide which is best for your implementation. As a quick high-level reference, AWS offers a Cloud Compute Index, which can be found using the link on screen. And this shows different examples and scenarios of where you might use different compute deployment units. That brings me to the end of this very short lecture. Now we are aware of what compute is, let's start by looking at some of the services offered by AWS that provide this compute resource, starting with Elastic Cloud Compute, EC2. Hello and welcome to this lecture where I will explain what the EC2 service is and does and how to configure an EC2 instance. So let's get started. As EC2 is one of the most common compute services used within AWS, I will discuss this service in greater detail over the other services that we'll cover in this course. EC2 is arguably the first compute service that you will encounter when working with AWS. It allows you to deploy virtual servers within your AWS environment, and most people will require an EC2 instance within their environment as a part of at least one of their solutions. There are a number of elements in creating your EC2 instance, which I want to break down and explain. This will hopefully help to define how the service works and answer a number of the questions that you may have. The EC2 service can be broken down into the following components: Amazon machine images, AMIs, instance types, instance purchasing options, tenancy, user data, storage options, and security. Let's look at each of these individually. The first point I want to cover are AMIs, Amazon Machine Images. These are essentially templates of pre-configured EC2 instances which allow you to quickly launch a new EC2 instance based on the configuration within the AMI. This prevents you from having to install an operating system or any other common applications that you might need to install on a number of other EC2 instances. From a high-level perspective, an AMI is an image baseline that will include an operating system and applications along with any custom configuration. AWS provides a large number of AMIs covering different operating systems from Linux to Red Hat to Microsoft Windows, among others. When configuring your EC2 instance, selecting your AMI is the first configuration choice you'll need to make. You can also create your own AMI images to help you speed up your own deployments. For example, you would start with selecting an AWS AMI, let's say a Linux server, and then once it is up and running, you may then need to install a number of your own custom applications and make specific configuration changes. Now, if you needed another server to perform the same functionality, you could go through the same process of selecting a Linux AWS AMI and again manually installing your applications and making your configurations. Or, once you have made those changes on the first instance, you can then simply create a brand new AMI or template of that instance with all the applications installed and configurations already made. Then if you need another instance of the same configuration, all you would need to do is to select your custom AMI as the base image for your instance, and it will launch with Linux server, your custom applications already installed, and any configurations already made. As you can see, this has many benefits and certainly comes in useful when implementing autoscaling. In addition to both AWS managed and your customer managed AMIs, you could also select an AMI from the AWS Marketplace. The AWS Marketplace is essentially an online store that allows you to purchase AMIs from trusted vendors like Cisco, Citrix, AlertLogic, etc. These vendor AMIs may have specific applications and configurations already made, such as instances that are optimized with built-in security and monitoring tools or contain database migration systems. Lastly, community AMIs also exist, which are a repository of AMIs that have been created and shared by other AWS members. Let's now take a look at instance types. Once you have selected your AMI from any of the different sources already discussed, you must then select an instance type. An instance type simply defines the size of the instance based on a number of different parameters. These being ECUs. This defines the number of EC2 compute units for the instance. vCPUs. This is the number of virtual CPUs on the instance. Physical processor. This is the process speed used on the instance. Clock speed. It's clock speed in gigahertz. Memory. The amount of memory associated. Instance storage. This is the capacity of the local instance store volumes available. EBS optimized available. This defines if the instance supports EBS optimized storage or not. Network performance. This shows the performance level of rate of data transfer. IPv6 support. This simply indicates if the instance type supports IPv6. Process architecture. This shows the architecture type of the processor. AES-NI. This stands for Advanced Encryption Standard New Instructions, and it shows if the instance supports it for enhanced data protection. AVX. This indicates if the instance supports AVX, which is Advanced Vector Extensions, which are primarily used for applications focused on audio and video, scientific calculations, and 3D modeling analysis. And finally, Turbo, which shows if the instance supports Intel Turbo Boost and AMD Turbo Core technologies. The key parameters here to primarily be aware of for general usage of an EC2 instance could be summarized as vCPUs, memory, instance storage, and network performance. But obviously this really depends on your actual usage and application. Having this flexibility of varied instances allows you to select the most appropriate size or power of an instance that you need for optimal performance within your applications. These different instance types are categorized into different family types that offer distinct performance benefits, which again helps you to select the most appropriate instance for your needs. Within each of these instance families, you will have a range of instance types with varied CPU, memory, storage, and network performance, etc. These instance families can be summarized as follows. Micro instances. These instances have a low cost against them due to the minimal amount of CPU and memory power that they offer. These are ideal for very low throughput use cases such as low traffic websites. General purpose. Instance types within this family have a balanced mix of CPU, memory and storage, making them ideal for small to medium databases, test and development servers and back-end servers. Compute optimized. As the name implies, instance types within this family have a greater focus on compute. They have the highest performing processes installed, allowing them to be used for high performance front-end servers, web servers, high performance science and engineering applications, and video encoding and batch processing. GPU. GPU stands for Graphics Processing Unit, and so the instances within this family are optimized for graphic intensive applications. FPGA. This family of instances allows you to customize field programmable gate arrays to create application-specific hardware accelerations when used with applications that use massively parallel processing power, such as genomics and financial computing. Memory optimized. This family includes instance types that are primarily used for large-scale enterprise-class in-memory applications, such as performing real-time processing of unstructured data. They are also ideal for enterprise applications such as Microsoft SharePoint. These instances offer the lowest cost per gigabyte of RAM against all other instance families. Storage optimized. As expected, these are optimized for enhanced storage. Instances in this family use SSD-backed instance storage for low latency and very high I/O input-output performance, including very high IOPS, which is input-output operations per second, and these are great for analytic workloads and NoSQL databases, data file systems, and log processing applications. Instance purchasing options. You can purchase EC2 instances through a variety of different payment plans. These have been designed to help you save costs by selecting the most appropriate option for your deployment. The different EC2 payment options are as follows: on-demand instances, reserved instances, scheduled instances, spot instances, and on-demand capacity reservations. It's good to be aware of these different options, as by having an understanding of these can help you save a considerable amount of money depending on your use case. Let me run through each option to help explain. Starting with on-demand instances. These are EC2 instances that you can launch at any time and have it provisioned and available to you within minutes. You can use this instance for as short a time or for as long as you need before terminating the instance. These instances have a flat rate and is determined on the instance type selected and is paid by the second. On-demand instances are typically used for short-term uses where workloads can be irregular and where the workload can't be interrupted. Many users of AWS use on-demand instances within their testing and development environments. And when you stop or terminate your on-demand instance, you will stop paying for the compute resource. Reserved instances allow you to purchase a discount for an instance type with set criteria for a set period of time in return for a reduced cost compared to on-demand instances. This reduction can be as much as 75%. These reservations against instances must be purchased in either 1 or 3 year timeframes. Further reductions can be achieved with reserved instances depending on which payment methods you select. There are 3 options available to you. Firstly, all up front. The complete payment for the 1 or 3 year reservation is paid, and this offers the largest discount and no further payment is required regardless of the number of hours the instance is used. Partial upfront. Here a small upfront payment is made and then a discount is applied to all remaining hours during the term. And finally, no upfront. No upfront or partial payments are made and the smallest discount of the 3 models is applied to all remaining hours in the term. Reserved instances are used for long-term predictable workloads, allowing you to make full use of the cost savings to be had when using compute resources offered by EC2. Scheduled instances. These are similar to reserved instances in the fact that you pay for the reservations of an instance on a recurring schedule, either daily, weekly or monthly. For example, you might have a weekly task that is scheduled that performs some kind of bulk processing for a number of hours at the same time every week. With scheduled instances, you could set up a scheduled instance to run during that set time frame once a week, and this prevents you from having to use the on-demand instances, which would incur a higher price. You should note that when using scheduled instances, that even if you didn't use the instance, you would still be charged. This allows you to provision instances for scheduled workloads that are not continuously running, which is where a reserved instance would be the preferred choice. Spot instances allows you to bid for unused EC2 compute resources. However, your resource is not guaranteed for a fixed period of time. To use the spot instance, you must bid higher than the current spot price, which is set by AWS. And this spot price fluctuates depending on supply and demand of the unused resource. If your bid price for an instance type is higher than the spot price, then you'll purchase that instance. But as soon as your bid price becomes lower than the fluctuating spot price, you'll be issued a 2-minute warning before the instance automatically terminates and is removed from your AWS environment. The bonus for spot instances is that you can bid for large EC2 instances at a very low cost point, saving a huge amount on cost. Due to the nature of how the instances can be suddenly removed from your environment, spot instances are only useful for processing data and applications that can be suddenly interrupted, such as batch jobs and background processing of data. Capacity reservations allows you to reserve capacity for your EC2 instances based on different attributes, such as instance type, platform and tenancy, etc., within a particular availability zone for any period of time. This ensures that you always have the available number of instances you require within a specific availability zone immediately. This capacity reservation could also be used in conjunction with your reserved instances discount, providing you additional savings. Let me now talk to you about EC2 tenancy, and this relates to what underlying host your EC2 instance will reside on, so essentially the physical server within an AWS data center. Again, there are different options available to you, with pros and cons to each. Shared tenancy. This option will launch your EC2 instance on any available host with the specified resources required for your selected instance type, regardless of which other customers and users also have EC2 instances running on the same hosts. Hence, the shared tenancy name. AWS implement advanced security mechanisms to prevent one EC2 instance from accessing another on the same host. How this security is applied and operated is out of scope of this course, and it is maintained by AWS themselves. Dedicated tenancy. This includes both dedicated instances and dedicated hosts. Dedicated instances are hosted on hardware that no other customer can access. It can only be accessed by your own AWS account. You may be required to launch your instances as a dedicated instance due to internal security policies or external compliance controls. Dedicated instances do incur additional charges due to the fact you are preventing other customers from running EC2 instances on the same hardware, and so there will likely be unused capacity remaining. However, the hardware might be shared by other resources you have running in your own account. Dedicated hosts. A dedicated host is effectively the same as dedicated instances. However, they offer additional visibility and control how you can place your instances on the physical host. They also allow you to use your existing licenses, such as per VM license or Windows Server licenses, etc. Using dedicated hosts give you the ability to use the same host for a number of instances that you want to launch and align with any compliance and regulatory requirements. If you don't need to address any compliance or security issues that require dedicated tenancy, then I will recommend using shared tenancy to reduce your overall costs. User data. During the configuration of your EC2 instance, there is a section called User Data, which allows you to enter commands that will run during the first boot cycle of that instance. This is a great way to automatically perform functions upon boot, such as to pull down any additional software you want installing from any software repositories you may have. You could also download and get the latest OS updates during boot. For example, you could enter yum update-y for a Linux instance, which will then update its own software automatically at the time of boot. Storage options. As a part of the configuration when setting up an EC2 instance, you are asked to select and configure your storage requirements. Selecting storage for your EC2 instance will depend on the instance selected, what you intend to use the instance for, and how critical the data is. Storage for EC2 can be classified between two distinct categories: persistent storage and ephemeral storage. Ephemeral meaning temporary. Persistent storage is available by attaching elastic block storage, EBS volumes, and ephemeral storage is created by some EC2 instances themselves using local storage on the underlying host, known as instance-backed storage. Let's look at each of these storage options in greater depth. EBS volumes are separate devices from the EC2 instance itself, and so it's not physically attached like ephemeral storage is. EBS volumes are considered network-attached storage devices, which are then logically attached to the EC2 instance via the AWS network. This principle is not dissimilar to attaching an external hard disk to your home laptop or PC, where the external hard disk represents your EBS volume and your PC represents your EC2 instance. The data on EBS volumes are automatically replicated to other EBS volumes within the same availability zone for resiliency, which is managed by AWS. You can disconnect an EBS volume from your EC2 instance and the data will remain intact, allowing you to reattach it to another EC2 instance if required. You can also implement encryption on these volumes if needed and take backup snapshots of all the data on the volume to S3. EBS volumes can be created in different sizes, again with different performance capabilities depending on your requirements. Ephemeral storage, or instance-backed storage, is the storage that is physically attached to the underlying host on which the EC2 instance resides on. Looking back at our previous example, this would be similar to your own laptop or PC's hard disk. There is a difference here though. With AWS EC2 instances, as soon as the instance is stopped or terminated, all saved data on ephemeral storage is lost. If you reboot your instance, then the data will remain, but not if you stop it. Therefore, if you have data that you need to retain, it is not recommended that you use instance-backed storage for this data. Instead, use EBS volumes for persistent data storage. Unlike EBS volumes, you are unable to detach ephemeral instance store volumes from the instance. Security. Security is fundamental with any AWS deployment, and so I just want to highlight a couple of points relating specifically to EC2 security. Firstly, and during creation of your EC2 instance, you will be asked to select a security group for your instance. A security group is essentially an instance level firewall, allowing you to restrict both ingress and egress traffic by specifying what traffic is allowed to communicate with it. You can restrict this communication by source, ports, and protocols for both inbound and outbound communication. Your instances are then associated with this security group. More information on security groups can be found in my blog post, found here covering instance level security. At the very end of your EC2 instance creation, you'll need to select an existing key pair or create and download a new one. But what is a key pair and what is it used for? A key pair, as the name implies, is made up of two components, a public key and a private key. The function of key pairs is to encrypt the login information for Linux and Windows EC2 instances, and then decrypt the same information, allowing you to authenticate onto the instance. The public key encrypts data such as the username and password. For Windows instances, the private key is used to decrypt this data, allowing you to gain access to the login credentials, including the password. For Linux instances, the private key is used to remotely connect onto the instance via SSH. The public key is held and kept by AWS, and the private key is your responsibility to keep and ensure that it is not lost or compromised. So going back to when you create your EC2 instance and a new key pair, you are given the opportunity to download the key pair. Once you have done this, you must keep that file safe until you're ready to log on to the associated EC2 instance. It's worth noting that you can use the same key pair on multiple instances to save you managing multiple private keys. Do bear in mind, however, should the private key become compromised, access could be gained to all the instances where that key pair was used. Once you have authenticated to the EC2 instance the first time, you can set up additional less privileged access controls such as local Windows accounts, allowing other users to connect and authenticate to or even utilize Microsoft Active Directory. One final point regarding security on your EC2 instance, it is your responsibility to maintain and install the latest OS and security patches released by the OS vendor as dictated within the AWS shared responsibility model. More information on this can be found in this blog post. We have now covered the main elements of the EC2 service that should hopefully allow you to get started by creating your first EC2 instance and selecting the most appropriate configuration for your needs. But to reiterate what we have covered and make it all fit together, I will demonstrate how to create a new EC2 instance from within the console, quickly highlighting the elements we have discussed as I go through. Okay, so I'm logged into my AWS management console, and to start with we need to go to EC2, which is under the compute category. Now this will take us to the EC2 console, and from here we can simply select Launch Instance. Now this is the first stage of the configuration where we have to select our Amazon machine image, our AMI. And here are a number of AWS AMIs that they supply, covering Windows, Red Hat, Linux, etc. And on the left hand side there's just a few other options. If you've created any AMIs yourself, that would be stored here. I mentioned the AWS Marketplace earlier, and here you can see lots of different AMIs from other suppliers such as Trend Micro, Juniper Networks, Barracuda, etc. and also the community AMIs as well. So let's get started with the quick start and look at some of the AWS supplied AMIs, and I'm just going to launch this Amazon Linux box. So I'll select that as my AMI. Now we get to choose our instance type, and we can filter up here with different types of instance types, general purpose, compute optimized, etc. Just going to leave it as all. And then down here we can see the different families and the types, the vCPUs, memory, etc. that each of these has. So I'm going to leave it on the T2 Micro general purpose instance. So I'm going to select Next, Configure Instance Details. Now we have a number of options here. The number of instances that we want to launch, I'm just going to keep it as 1. If we want to launch this as a spot instance, then we can select this box here to do so. But I'm just going to create it as an on-demand instance. We can select our VPC that we want to run it in, and we'll have different VPCs there. You can then select the subnet if you'd like, and if you'd like to auto-assign a public IP address. We can assign a role to an EC2 instance if we need to, and we can also control the shutdown behavior. So when we shut down our EC2 instance, do we want to terminate that instance or just stop? I'm going to leave that as a default as stop. There's a couple of other controls you can put in here. Enable termination protection, and what that will do is that will prevent you from terminating your instance until you uncheck this box. And you can also enable detailed CloudWatch monitoring if you need to. With regards to tenancy, we discussed this earlier. It can either be shared or run as a dedicated instance or on a dedicated host. I'm going to leave that as shared. I'll leave all other options as default, and then I'll click on next to go to storage. This shows the current storage that comes with the AMI. We can see that it's 8 gig in size and it's a general purpose SSD drive. There's a tick box here to delete the volume on termination, and we can see that it's not encrypted. If we wanted to add a new volume, we can add an EBS volume here. Again, we can specify the size, 8 gig, or if you want to add it to 30, for example. And then we can also, again, delete on termination, and we have the option to encrypt the EBS volume if we wanted to. It's by selecting the default AWS EBS encryption key. So now we have 2 drives. One of them is the root volume and an additional drive, which is an EBS volume. If we click on next, add tags. Here we can add a key value pair tag to this instance. So for example, add a key of name and a value of my instance. And we can add additional tags as well. As you can see here, we can add up to 50 tags if we wanted to. So we can add a project that it belongs to, or the cost center, etc. Any tags that make it more usable to you. Once you've finished adding your tags, click on Configure Security Group. And this is where we control what can and can't access your instance. Now you can create a new security group or select an existing security group that you might already have. If we create a new security group and call it My Security Group, then you can add a description. And here are the rules for the security group. So at the moment we have SSH using TCP across port 22. And you can have the source as a custom IP address range or a single IP address. So you might just want a specific subnet in your VPC to talk to this instance. Or you can have anywhere. Or you can have just your own IP address. Let's put in a custom IP address range of 10.0.1.0/24. And again, you can add a description in there if you want to. You can add a new rule. For example, HTTP traffic. And again, you can add your source, say anywhere. Then once you're happy with your security groups, click on Review and Launch. And this just provides a summary of all the configuration options that you made up to this point. If you need to edit any of the details, you can just click on the right hand side here, edit the instance type, the security groups, etc. Once you're happy with all of your information, click on Launch. And this is where you can select or create a new key pair to connect to your instance. So let's go ahead and create a new key pair. Call it My Instance. And now I need to download this key pair, which will download the private part. Once that key pair is downloaded, I can then click on Launch Instance. Now, if we go back to our dashboard by clicking on View Instances, we can see here that it's trying to launch at the minute. The status is pending, and it shouldn't take too long for that to become active. And here we go. We can now see it's up and running. Before I finish this demonstration, I just want to point out one last point relating to status checks that we can see from within our EC2 dashboard. These status checks are used to check the health and status of your EC2 instance, and understanding what common faults could trigger these checks to fail can help you troubleshoot issues with your EC2 resources. There are 2 types of status checks: system status checks and instance status checks. If the system status check fails, then it is likely to be an issue with the underlying host rather than a configuration issue with your EC2 instance. Common issues that trigger system status checks to fail are loss of power, loss of network connectivity, and hardware and software issues on the underlying host. Basically, a system status check failure is out of our control as the fault lies with components that AWS are responsible for. The best way to resolve this would be to stop the instance and restart. This is likely to cause the instance to launch on another physical host, resolving the problem. Do not reboot the instance, as this will cause the instance to continue running on the same physical server. Instance status checks. These differ from system status checks, as if this fails, then it will likely require your input to help and resolve the issue. This check looks at the EC2 instance itself rather than focusing on the underlying host. Common issues that trigger these checks to fail are incorrect network configuration, corrupt file systems, exhausted memory, or an incompatible kernel. These faults will require you to troubleshoot and resolve the issue, for example, changing the network configuration. If you'd like some hands-on experience with EC2, then we do offer 2 labs in which you can practice creating your own EC2 instances for both Linux and Windows. That now brings me to the end of this lecture on EC2. Like I mentioned previously, this is going to be the longest and most in-depth lecture, simply due to how much of a key compute service it is in a wide range of use cases. Hello and welcome to this short lecture which will provide a high-level overview of the Amazon EC2 container service, commonly known as Amazon ECS. This service allows you to run Docker-enabled applications packaged as containers across a cluster of EC2 instances without requiring you to manage a complex and administratively heavy cluster management system. The burden of managing your own cluster management system is abstracted with the Amazon ECS service by passing that responsibility over to AWS, specifically through the use of AWS Fargate. If you're new to some of these terms, such as Docker, containers, and AWS Fargate, then let me quickly in a single sentence define what they are to help you understand the service a little easier. AWS Fargate is an engine used to enable ECS to run containers without having to manage and provision instances and clusters for containers. Docker is a piece of software that allows you to automate the installation and distribution of applications inside Linux containers. So what are containers? A container holds everything that an application requires to enable it to run from within its isolated container package. This may include system libraries, code, system tools, runtime, etc. But it does not include an operating system like a virtual machine does, and so reduces overhead of the actual container itself. Containers are decoupled from the underlying operating system, making container applications very portable, lightweight, flexible and scalable across a cloud environment. This ensures that the application will always run as expected regardless of its deployment location. With this in mind, if you are already using Docker or have existing containerized applications packaged locally, then these will work seamlessly on Amazon ECS. For more information on Docker and containers, please see our existing content found here. Let's now take a deeper look at the EC2 container service and some of the additional functions that it provides. As I mentioned before, EC2 container service removes the need for you to manage your own cluster management system thanks to its interaction with AWS Fargate. You don't even have to specify which instance type to use. This can be very time consuming and requires a lot of overhead to continually monitor and maintain and scale. With Amazon ECS, there is no need to install any management software for your cluster, neither is there a need to install any monitoring software either. All of this and more is taken care of by the service, allowing you to focus on building great applications and deploying them across your scalable cluster. When launching your ECS cluster, you have the option of 2 different deployment models, a Fargate launch and an EC2 launch. The Fargate launch requires far less configuration and simply requires you to specify the CPU and memory required, define the networking and IAM policies, in addition to you having to package your applications in containers. However, with an EC2 launch, you have a far greater scope of customization and configurable parameters. For example, you are responsible for patching and scaling your instances, and you can specify which instance type to use and how many containers should be in a cluster. There are use cases for both modes. You may need more granularity and control with some of your clusters due to security and compliance controls. Monitoring is taken care of through the use of AWS CloudWatch, which will monitor metrics against your containers and your cluster. Those of you who have used CloudWatch before will be aware that you can easily create alarms based off of these metrics, providing you notification of when specific events occur, such as your cluster size scaling up or down. An Amazon ECS cluster is comprised of a collection of EC2 instances. As such, some of the functionality and features that we have already discussed in this course can be used with these instances. For example, security groups to implement instance level security at a port and protocol level, along with elastic load balancing and auto-scaling. Although these EC2 instances form a cluster, they still operate in much the same way as a single EC2 instance. So again, for example, should you need to connect to one of your instances itself, you could still use the same familiar methods, such as initiating an SSH connection. The clusters themselves act as a resource pool, aggregating resources such as CPU and memory. The cluster is dynamically scalable, meaning you can start your cluster as a single small instance, but it can dynamically scale to thousands of larger instances. Multiple instance types can be used within the cluster if required. Although the cluster is dynamically scalable, it's important to point out that it can only scale within a single region. Amazon ECS is region specific, so it can span multiple availability zones, but it cannot span multiple regions. With ECS, you can schedule your containers to be deployed across your cluster based on different requirements, such as resource requirements or specific availability requirements through the use of multiple availability zones. The instances within the Amazon ECS cluster also have a Docker daemon and an ECS agent installed. These agents communicate with each other, allowing Amazon ECS commands to be translated into Docker commands. Hello and welcome to this lecture covering the Elastic Container Registry service known as ECR. This service links closely with the previous service discussed, the EC2 container service, as it provides a secure location to store and manage your Docker images that can be distributed and deployed across your applications. This is a fully managed service, and as a result, you do not need to provision any infrastructure to allow you to create this registry of Docker images. This is all provisioned and managed by AWS. This service is primarily used by developers, allowing them to push, pull and manage their library of Docker images in a central and secure location. To understand the service better, let's look at some of the components used. These being the registry, authorization token, repository, repository policy and image. Let's take a look at the registry first. The ECR registry is the object that allows you to host and store your Docker images in, as well as create image repositories. Within your AWS account, you will be provided with a default registry. When your registry is created, then by default the URL for the registry is as follows, where you will need to replace the red text with your own information that's applicable to your account and region. Your account will have both read and write access by default to any images you create within the registry and any repositories. Access to your registry and images can be controlled via IAM policies in addition to repository policies as well, to enforce tighter and stricter security controls. As the Docker command line interface doesn't support the different AWS authentication methods that are used, then before your Docker client can access your registry, it needs to be authenticated as an AWS user, which will then allow your client to both push and pull images, and this is done by using an authorization token. To begin the authorization process to allow your Docker client to communicate with your default registry, you can run the get login command using the AWS CLI as shown, where the red text should be replaced with your own region. This will then produce an output response, which will be a Docker login command. You must then copy this command and paste it into your Docker terminal, which will then authenticate your client and associated Docker CLI to your default registry. This process produces an authorization token that can be used within the registry for 12 hours, at which point you will need to re-authenticate by following the same process. The repository are objects within your registry that allow you to group together and secure different Docker images. You can create multiple repositories with the registry, allowing you to organize and manage your Docker images into different categories. Using policies from both IAM and repository policies, you can assign set permissions to each repository, allowing specific users to perform certain actions, such as performing a push or pull API. As I just mentioned, you can control access to your repositories and images using both IAM policies and repository policies. There are a number of different IAM managed policies to help you control access to ECR, these being the three shown on the screen. For more information on IAM and policies, please refer to our existing course here, which covers IAM and policy creation and management. Repository policies are resource-based policies, which means you need to ensure you add a principal to the policy to determine who has access and what permissions they have. It's important to be aware of that for an AWS user to gain access to the registry, they will require access to the ECR Get Authorization Token API call. Once they have this access, repository policies can control what actions those users can perform on each of the repositories. These resource-based policies are created within ECR itself and within each of the repositories that you have. Once you have configured your registry, repositories and security controls and authenticated your Docker client with ECR, you can then begin storing your Docker images in the required repositories, ready to then pull down again as and when required. To push an image into ECR, you can use the Docker push command, and to retrieve an image, you can use the Docker pull command. For more information on how to form both a push and a pull of images, please see the following links. That now brings me to the end of this lecture covering the Elastic Container Registry service. Coming up in the next lecture, I shall be looking at the Amazon Elastic Container Service for Kubernetes, known as EKS. Hello and welcome to this lecture covering the Elastic Container Service for Kubernetes, more commonly known as EKS. Firstly, for those unfamiliar with Kubernetes, let me briefly explain what it is at a high level. Kubernetes is an open source container orchestration tool designed to automate, deploy, scale and operate containerized applications. It is designed to grow from tens, thousands or even millions of containers. Kubernetes is also container runtime agnostic, which means you can actually use Kubernetes to run Rocket and Docker containers. So back to EKS. With EKS, AWS provides a managed service allowing you to run Kubernetes across your AWS infrastructure without having to take care of provisioning and running the Kubernetes management infrastructure in what's referred to as the control plane. You, the AWS account owner, only need to provision and maintain the worker nodes. So what is a control plane and what are worker nodes? Kubernetes control plane. There are a number of different components that make up the control plane, and these include a number of different APIs, the kubelet processes, and the Kubernetes master, and these dictate how Kubernetes and your clusters communicate with each other. The control plane itself is run across master nodes. The control plane schedules containers onto nodes. The term scheduling does not refer to time in this context. Scheduling in this case refers to the decision process of placing containers onto nodes in accordance with their declared compute requirements. The control plane also tracks the state of all Kubernetes objects by continually monitoring the objects. So in EKS, AWS is responsible for provisioning, scaling, and managing the control plane, and they do this by utilizing multiple availability zones for additional resilience. Worker nodes. Kubernetes clusters are composed of nodes, and the term cluster refers to the aggregate of all the nodes. A node is a worker machine in Kubernetes and runs as an on-demand EC2 instance and includes software to run containers managed by the Kubernetes control plane. For each node created, a specific AMI is used, which also ensures Docker and the kubelet in addition to the AWS IAM authenticator is installed for security controls. These nodes are what us as the customers are responsible for when managing and working with EKS. Once the worker nodes are provisioned, they can then connect to EKS using an endpoint. For more information on Kubernetes, please see our existing course, Introduction to Kubernetes, found here. Let me provide a brief overview of what's required to start using the EKS service. Firstly, you need to create an EKS service role. Before you begin working with EKS, you need to configure and create an IAM service role that allows EKS to provision and configure specific resources. This role needs only to be created once and can be used for all other EKS clusters created going forward. The role needs to have the following permissions policies attached to the role: the Amazon EKS service policy and the Amazon EKS cluster policy. Next, you need to create an EKS cluster VPC. Using AWS CloudFormation, you need to create and run a CloudFormation stack based on the following template. And this will configure a new VPC for you to use with EKS. Thirdly, you need to install the kubectl and the AWS IAM authenticator. kubectl is a command line utility for Kubernetes and can be installed following the details supplied here. The IAM authenticator is required to authenticate with the EKS cluster, depending on your client OS, Linux, macOS or Windows, and this can be downloaded using the links on screen. Next, you need to create your EKS cluster. Using the EKS console, you can now create your EKS cluster using the details and information from the VPC created in step 1 and 2. Next, you must configure the kubectl for EKS. Using the update kubeconfig command via the AWS CLI, you need to create a kubeconfig file for your EKS cluster. Next, provision and configure worker nodes. Once your EKS cluster shows an active status, you can launch your worker nodes using CloudFormation based on the following template. And finally, you need to configure the worker node to join the EKS cluster. Using a configuration map downloaded here, you must edit it and replace the ARN of the instance role, not the instance profile, with the node instance role value from step 6. Your EKS cluster and worker nodes are now configured, ready for you to deploy your applications with Kubernetes. For more information on EKS, please see our existing course, Introduction to EKS, which will cover these points and more in greater detail. Hello and welcome to this lecture on AWS Elastic Beanstalk. AWS Elastic Beanstalk is an AWS managed service that allows you to upload the code of your web application along with the environment configurations, which will then allow Elastic Beanstalk to automatically provision and deploy the appropriate and necessary resources required within AWS to make the web application operational. These resources can include other AWS services and features such as EC2, auto-scaling, application health monitoring, and elastic load balancing, in addition to capacity provisioning. This automation and simplification makes it an ideal service for engineers who may not have the familiarity or the necessary skills within AWS to deploy, provision, monitor, and scale the correct environment themselves to run the developed applications. Instead, this responsibility is passed on to AWS Elastic Beanstalk to deploy the correct infrastructure to run the uploaded code. This provides a simple, effective, and quick solution to deploying your web application. Once the application is up and running, you can continue to support and maintain the environment as you would with a custom-built environment. You can additionally perform some of the maintenance tasks from the Elastic Beanstalk dashboard itself. Elastic Beanstalk is able to operate with a variety of different platforms and programming languages, making it a very flexible service for your DevOps teams. Currently, at the time of writing this course, Elastic Beanstalk is compatible with the following. One important point to note is that the service itself is free to use. There is no cost associated with Elastic Beanstalk. However, any resources that are created on your application's behalf, such as EC2 instances, you will be charged for as per the standard pricing policies at the time of deployment. So now we know at a high level what AWS Elastic Beanstalk is and does, let me run through some of its core components that creates the service. The application version. An application version is a very specific reference to a section of deployable code. The application version will point typically to S3, the simple storage service, to where the deployable code may reside. The environment. An environment refers to an application version that has been deployed on AWS resources. These resources are configured and provisioned by AWS Elastic Beanstalk. At this stage, the application is deployed as a solution and becomes operational within your environment. The environment is comprised of all the resources created by Elastic Beanstalk and not just an EC2 instance with your uploaded code. Environment configurations. An environment configuration is a collection of parameters and settings that dictate how an environment will have its resources provisioned by Elastic Beanstalk and how these resources will behave. The environment tier. This component reflects on how Elastic Beanstalk provisions resources based on what the application is designed to do. If the application manages and handles HTTP requests, then the app will be run in a web server environment. If the application does not process HTTP requests and instead perhaps pulls data from an SQS queue, then it would run in a worker environment. I shall cover more on the differences between the web server and worker environments shortly. The configuration template. This is the template that provides the baseline for creating a new, unique environment configuration. Platform. The platform is a culmination of components in which you can build your application upon using Elastic Beanstalk. These comprise of the operating system of the instance, the programming language, the server type, web or application, and components of Elastic Beanstalk itself, and as a whole can be defined as a platform. Applications. Within Elastic Beanstalk, an application is a collection of different elements, such as environments, environment configurations, and application versions. In fact, you can have multiple application versions held within a single application. You can deploy your application across one of two different environment tiers, either the web server tier or the worker tier. These tiers are configured differently depending on the use case of your application. The web server environment is typically used for standard web applications that operate and serve requests over HTTP port 80. This tier will typically use service and features such as Route 53, elastic load balancing, auto-scaling, EC2 and security groups. The worker environment is slightly different and are used by applications that will have a back-end processing task that will interact with AWS SQS, the simple queue service. This tier typically uses the following AWS resources in this environment: an SQS queue, an IAM service role, auto-scaling and EC2. Now you are aware of some of the terminology and components, we can look at how AWS Elastic Beanstalk operates a very simple workflow process for your application deployment and ongoing management in what can be defined in 4 simple steps. Firstly, you create an application. Next, you must upload your application version of the application to Elastic Beanstalk, along with some additional configuration information regarding the application itself. This creates the environment configuration. The environment is then created by Elastic Beanstalk with the appropriate resources to run your code. Any management of your application can then take place, such as deploying new versions of your application. If the management of your applications have altered the environment configuration, then your environment will automatically be updated to reflect the new code should additional resources be required. For further information and to get some hands-on experience with AWS Elastic Beanstalk to deploy an application, take a look at our 2 labs which will guide you through the steps and processes we have discussed. That now brings us to the end of this lecture. Coming up next, I will introduce you to AWS Lambda. Hello and welcome to this lecture where we shall take an introductory look at AWS Lambda. AWS Lambda is a serverless compute service which has been designed to allow you to run your application code without having to manage and provision your own EC2 instances. This saves you having to maintain and administer an additional layer of technical responsibility within your solution. Instead, that responsibility is passed over to AWS to manage for you. Essentially, serverless means that you do not need to worry about provisioning and managing your own compute resource to run your own code. Instead, this is managed and provisioned by AWS. AWS will start, scale, maintain and stop the compute resources as required, which can be just as short as just a few milliseconds. Although it's named serverless, it does of course require servers or at least compute power to carry out your code requests. But because the AWS user does not need to be concerned with what's managing this compute power or where it's provisioned from, it's considered serverless from the user perspective. If you don't have to spend time operating, managing, patching and securing an EC2 instance, then you have more time to focus on the code of your application and its business logic, while at the same time optimizing costs. With AWS Lambda, you only ever have to pay for the compute power when Lambda is in use via Lambda functions, and I shall explain more on these later. AWS Lambda charges compute power per 100 milliseconds of use only when your code is running, in addition to the number of times your code runs. With sub-second metering, AWS Lambda offers a truly cost-optimized solution for your serverless environment. So how does it work? Well, there are essentially 4 steps to its operation. Firstly, AWS Lambda needs to be aware of your code that you need to run, so you can either upload this code to AWS Lambda or write it within the code editor that Lambda provides. Currently, AWS Lambda supports Node.js, JavaScript, Python, Java, Java 8 compatible, C#, .NET Core, Go, and also Ruby. It's worth mentioning that the code that you write or upload can also include other libraries. Once your code is within Lambda, you need to configure Lambda functions to execute your code upon specific triggers from supported event sources, such as S3. As an example, a Lambda function can be triggered when an S3 event occurs, such as an object being uploaded to an S3 bucket. Once the specific trigger is initiated during your normal operations of AWS, AWS Lambda will run your code as per your Lambda function, using only the required compute power as defined. Later in this course, I will cover more on when and how this compute power is specified. AWS records the compute time in milliseconds and the quantity of Lambda functions run to ascertain the cost of the service. For an AWS Lambda application to operate, it requires a number of different elements. The following form the key constructs of a Lambda application. Lambda function. The Lambda function is compiled of your own code that you want Lambda to invoke as per defined triggers. Event source. Event sources are AWS services that can be used to trigger your Lambda functions. Or put another way, they produce the events that your Lambda function essentially responds to by invoking it. For a comprehensive list of these event sources, please see the following link on the screen. Trigger. A trigger is essentially an operation from an event source that causes the function to invoke, so essentially triggering that function. For example, an Amazon S3 put request could be used as a trigger. Downstream resources. These are the resources that are required during the execution of your Lambda function. For example, your function might call upon accessing a specific SNS topic or a particular SQS queue. So they are not used as the source of the trigger, but instead they are the resources to be used to execute the code within the function upon invocation. Log streams. In an effort to help you identify issues and troubleshoot issues with your Lambda function, you can add logging statements to help you identify if your code is operating as expected into a log stream. These log streams would essentially be a sequence of events that all come from the same function and recorded in CloudWatch. In addition to log streams, Lambda also sends common metrics of your functions to CloudWatch for monitoring and alerting. At a high level, the configuration steps for creating a Lambda function via the AWS Management Console could consist of selecting a blueprint, and AWS Lambda provides a large number of common blueprint templates which are pre-configured Lambda functions. To save time in your own code, you can select one of these blueprints and then customize it as necessary. An example of one of these blueprints could be the S3 get object, which is an Amazon S3 trigger that retrieves metadata for the object that has been updated. You then need to configure your triggers, and as I just explained, the trigger is an operation from an event source that causes the function to invoke. And in my previous statement, I suggested an S3 put request. And then you need to finish configuring your function. And this section requires you to either upload your code or edit it in line. And it also requires you to define the required resources, the maximum execution timeout, the IAM role, and handler name. A key benefit of using AWS Lambda is that it is a highly scalable serverless service, coupled with fantastic cost optimization compared to EC2, as you are only charged for compute power while the code is running and for the number of functions called. For more information on AWS Lambda and how to configure it in detail can be found in our following course. For your own hands-on experience with AWS Lambda, please take a look at our labs which will guide you through how to create your first Lambda function. That now brings me to the end of this lecture covering AWS Lambda. Coming up next, I shall be discussing AWS Batch. Hello and welcome to this lecture where I'll provide a high-level overview of AWS Batch. As the name suggests, this service is used to manage and run batch computing workloads within AWS. Before we go any further, I just want to quickly clarify what batch computing is. Batch computing is primarily used in specialist use cases which require a vast amount of compute power across a cluster of compute resources to complete batch processing, executing a series of jobs or tasks. Outside of a cloud environment, it can be very difficult to maintain and manage a batch computing system. It requires specific software and requires the ability to consume the resources required, which can be very costly. However, with AWS Batch, many of these constraints, administration activities, and maintenance tasks are removed. You can seamlessly create a cluster of compute resources which is highly scalable, taking advantage of the elasticity of AWS, coping with any level of batch processing while optimizing the distribution of the workloads. All provisioning, monitoring, maintenance and management of the clusters themselves is taken care of by AWS, meaning there is no software to be installed by yourself. There are effectively 5 components that make up AWS Batch Service, which will help you to start using the service. These being jobs. A job is classed as a unit of work that is to be run by AWS Batch. For example, this can be a Linux executable file, an application within an ECS cluster, or a shell script. The jobs themselves run on EC2 instances as a containerized application. Each job can at any one time be in a number of different states, for example, submitted, pending, running, failed, among others. Job definitions. These define specific parameters for the jobs themselves. They dictate how the job will run and with what configuration. Some examples of these may be how many vCPUs to use for the container, which data volumes should be used, which IAM role should be used, allowing access for AWS Batch to communicate with other AWS services, and mount points. Job queues. Jobs that are scheduled are placed into a job queue until they run. It's also possible to have multiple queues with different priorities if needed. One queue could be used for on-demand EC2 instances, and another queue could be used for spot instances. Both on-demand and spot instances are supported by AWS Batch, allowing you to optimize cost, and AWS Batch can even bid on your behalf for those spot instances. Job scheduling. The job scheduler takes control of when a job should be run and from which compute environment. Typically, it will operate on a first-in, first-out basis, and it will look at the different job queues that you have configured, ensuring that higher priority queues are run first, assuming all dependencies of that job have been met. Compute environments. These are the environments containing the compute resources to carry out the job. The environment can be defined as managed or unmanaged. A managed environment means that the service itself will handle provisioning, scaling, and termination of your computer instances based on the configuration parameters that you would enter regarding the instance type, purchase method, such as on-demand or spot. This environment is then created as an Amazon ECS cluster. Unmanaged environments are provisioned, managed, and maintained by you, which gives greater customization. However, it does require greater administration and maintenance, and also requires you to create the necessary Amazon ECS cluster that the managed environment would have done on your behalf. If you have a requirement to run multiple jobs in parallel using batch computing, for example, to analyze financial risk models, perform media transcoding, or engineering simulations, then AWS Batch would be a perfect solution. Hello and welcome to this short lecture covering Amazon Lightsail. This is another compute service that in some respect closely resembles EC2 out of all the other compute resources we have covered so far. Amazon Lightsail is essentially a virtual private server, a VPS, backed by AWS infrastructure, much like an EC2 instance, but without as many configurable steps throughout its creation. It has been designed to be simple, quick, and very easy to use at a low cost point for small-scale use cases by small businesses or for single users. With its simplicity and small-scale use, it's commonly used to host simple websites, small applications, and blogs. You can run multiple Lightsail instances together, allowing them to communicate, and it's even possible, if required, to connect it to other AWS resources and to your existing VPC running within AWS via a peering connection. To deploy a Lightsail instance, it's easy to do all from a single page with just a few configuration options. Amazon Lightsail can be accessed either via the AWS console under the compute category, or you can go directly to the home page of AWS Lightsail, which sits outside of the management console and can be found here. If you want to launch a new instance, select Create Instance, where you can then create your instance all from just one page of options. Nice and simple. Firstly, you need to select your region and availability zone as required as to where you would like to provision your Lightsail instance. Next, you can select your platform, Linux or Windows based, and an additional blueprint if required. If you didn't need a blueprint, you can simply select to use the operating system only. Next, you have the option to add a launch script and a different key pair. The launch script can be a shell script that will run at the time of the launch, much like user data for an EC2 instance. By default, you are provided with a key pair to connect to your instance. However, you can select to choose an alternative one if required. Following this, you must then select your instance plan. This section defines the resources of your instance and how much you are going to be paying on a monthly basis. The price per month option shows preset configurations based on memory, processing power, storage, and data transfer. However, you can tab through the corresponding tabs and customize the values of each to meet your needs. As you can see, it's very clear, simple, and obvious as to what you will be paying and the resources you will get in return. The instances are charged as an on-demand price, so you will only pay for the resource when you are using them. The dollar per month price is based on having the instance on continuously, which AWS calculates as 31.25 days multiplied by 24 hours. The configuration options requires you to provide a unique name for your Lights Out instance. In addition to this, you're also prompted to add key value tags to help organize your resources. Now all of your configuration is complete, simply click on Create Instance. As you can see, it's very easy and simple to create your Lights Out VPS compared to the number of different screens and configuration options required when deploying an EC2 instance. Once your Amazon Lights Out service is up and running, you then have a number of management and monitoring options which are clear and easy to use. Connect. This option allows you to connect to your newly created instance using SSH, either via the inline SSH software provided by Lights Out or with your own SSH software using the key pair provided. The instance is given a public IP address to allow you to connect. Storage. This provides an overview of your current storage, showing the capacity and the disk path. For example, /dev/SDA1. You also have the ability to attach additional disks to your instance. Metrics. This allows you to view graphical metrics of your instance, such as CPU utilization, network in, network out, status check failed instance, and status check failed system. These graphs can be viewed over a number of different time periods, from 1 hour through to 2 weeks. Networking. The Networking tab allows you to view your IP address information along with a very simple virtual firewall, allowing you to control which ports your instance can accept connections from. You can also gain additional information on load balancing your traffic between instances. Snapshots. This provides a simple way to back up your instance. Tags. Here you can configure additional or edit existing tags to help you filter and organize your resources. Key value tags can also be used to help manage your billing and control access. History. This provides simple audit information of your instance, such as the date and time the instance was created or when configuration changes occurred. Delete. When you have finished with your instance, this tab allows you to delete your instance along with any data that was stored on it. As you can see, Amazon Lights Out provides a lightweight solution for small projects and use cases, which can be deployed quickly and cost effectively in just a few clicks. That brings us to the end of this lecture. Coming up next, I'll provide a summary of the key points and topics that we've learned throughout this course. Hello and welcome to this final lecture where I just want to quickly summarise what we have learned throughout this course. I started off by covering what is meant by compute resources, whereby I explained that compute resources can be considered the brains and processing power required by applications and systems to carry out computational abilities via a series of instructions. So essentially, compute is closely related to common server components, which many of you will be more familiar with, such as CPUs and RAM. Following this, we started to get into the meat of the AWS compute resources to provide you with an understanding of the fundamentals of the different compute services and features, which are Elastic Compute Cloud, EC2, Amazon ECS, which is the EC2 container service, Amazon Elastic Container Registry, ECR, Amazon Elastic Container Service for Kubernetes, EKS, AWS Elastic Beanstalk, AWS Lambda, AWS Batch, and Amazon Lightsail. During the EC2 lecture, we learned that it was one of the most common compute services in use today and what it provides from a compute perspective. I also discussed the different components of the service, covering Amazon Machine Images, AMIs, instance types, instance purchasing options, tenancy, user data, storage options, and security. I then performed a demonstration that showed you how to create a new EC2 instance from within the console. The next service we looked at was the Amazon EC2 Container Service, known as ECS. This can be defined as a service that allows you to run Docker-enabled applications packaged as containers across a cluster of EC2 instances without requiring you to manage a complex and administratively heavy cluster management system. As a result, there is no need to install any management software for your cluster, neither is there a need to install any monitoring software either. All of this and more is taken care of by the service, allowing you to focus on building great applications and deploying them across your scalable cluster. Following ECS, I gave an overview of the Elastic Container Registry, known as ECR. ECR is a fully managed service that provides a secure location to store and manage your Docker images that can be distributed and deployed across your applications. With ECR, you do not need to provision any infrastructure to allow you to create a registry of Docker images. This is all provided and managed by AWS. This service is primarily used by developers, allowing them to push, pull, and manage their library of Docker images in a central and secure location. The main components of ECR are the registry, authorization tokens, repository policies, and images. Next, I looked at the Elastic Container Service for Kubernetes, known as EKS. EKS provides a managed service allowing you to run Kubernetes across your AWS infrastructure without having to take care of provisioning and running the Kubernetes management infrastructure in what's referred to as the control plane. You, the AWS account owner, only need to provision and maintain the worker nodes. The control plane dictates how Kubernetes and your clusters communicate with each other and tracks the state of all Kubernetes objects by continually monitoring the objects. Worker nodes run as on-demand EC2 instances and include software to run containers managed by the Kubernetes control plane. For each node created, a specific AMI is used, which also ensures Docker and the kubelet in addition to the AWS IAM Authenticator is installed for security controls. To get started with EKS, you must perform the following steps. Create an EKS service role, create an EKS cluster VPC, install the kubectl and the AWS IAM Authenticator, create your EKS cluster, configure kubectl for EKS, provision and configure worker nodes, and configure the worker node to join the EKS cluster. Following on from EKS, I covered Elastic Beanstalk, which is an AWS managed service that takes your uploaded web application code and automatically provisions and deploys the required resources within AWS to make the web application operational. The components that make up Elastic Beanstalk include application versions, environments, environment configurations, environment tiers, configuration template, platform, and applications. I then covered how AWS Elastic Beanstalk operates a very simple workflow process for your application deployment in 4 simple steps. Firstly, you create an application. Next, you must upload your application version of the application to Elastic Beanstalk. The environment is then created by Elastic Beanstalk with the appropriate resources to run your code, and then any management of your application can then take place. Next was an overview of AWS Lambda, which is a service that lets you run your code in response to events in a scalable and highly available serverless environment. To reiterate again, serverless means that you do not need to worry about provisioning and managing your own compute resource to run your own code. Instead, this is managed and provisioned by AWS. Although it's named serverless, it does of course require servers or at least compute power to carry out your code requests. But because the AWS user does not need to be concerned with what compute is used or where it's coming from, it's considered serverless from the user perspective. I explained some of the components of Lambda, which included the Lambda function, the event source, downstream resources, and log streams. Once we understood what Lambda functions were, I covered how to create them and the 3 simple steps to do so, where you can select a blueprint, configure your triggers, and configure the function details. Following Lambda, I introduced AWS Batch, which is used to manage and run batch computing workloads within AWS. Batch computing is primarily used in specialist use cases which require a vast amount of computer power across a cluster of compute resources to complete batch processing, executing a series of jobs or tasks. To understand how AWS Batch worked, I covered some of the key parts. Jobs. A job is classed as a unit of work that is to be run by AWS Batch. Job definitions. These define specific parameters for the jobs themselves. Job queues. These are jobs that are scheduled and placed into a job queue until they run. Job scheduling. The job scheduler takes care of when a job should be run and from which compute environment. And compute environments. These are the environments containing the compute resources to carry out the job. Finally, we'll look at Amazon Lightsail, which provides a virtual private server, and it has been designed to be simple, quick, and very easy to use at a low cost point for small-scale use cases by small businesses or single users. With its simplicity and small-scale uses, it's commonly used to host simple websites, small applications, and blogs. And you can run multiple Lightsail instances together, allowing them to communicate, and it's even possible, if required, to connect it to other AWS resources and to your existing VPC running within AWS via a peering connection. An Amazon Lights Out instance can be launched and configured all from a single page, making this a simple solution. You should now have a good understanding of the different AWS compute services and features available, allowing you to select the most appropriate service for your project. Each have their advantages by providing something of value that's different to the others. If you have any feedback on this course, positive or negative, please contact us by sending an email to support@cloudacademy.com. Your feedback is greatly appreciated. Thank you for your time and good luck with your continued learning of cloud computing. Thank you.